Good evening, students. So let us move ahead with the biasing of the PN junction. So basically there are two types of biasing, the forward biasing and the reverse biasing. So in this video, in this lecture, we will be studying about the forward biasing. So what is biasing? When we connect a battery to the PN junction diode or PN junction, then it is termed as biasing of the PN junction. So when a positive terminal is connected to the p-type semiconductor and a negative terminal is connected to the n-type semiconductor, then the biasing so obtained is known as forward biasing. When the positive terminal of the battery is connected to the p-type semiconductor and the negative terminal of the battery is connected to the n-type semiconductor, then the biasing so obtained is known as the forward biasing. Okay, it is obtained the forward biasing. So here is my PN junction having a potential barrier which is formed with accumulated charges, opposite accumulated charges, and so it acts as a potential barrier for the PN junction diode. So it acts as a barrier for the PN junction diode. So we already know that in the p-type semiconductor, the majority charges are the holes or the positive charges and the minority are the electrons. And in the n-type semiconductor, the majority charges are the electrons and the minority are the holes, or we can say the holes, or we can say it as positive charges. Okay, so what will happen? The positive holes from here, because it is having the positive terminals. So in the positive terminals, the positive charges will be there. So these charges will move over here and they will get repelled by these holes. They will get repelled by these holes, and so they will exert a pressure on this p-type semiconductor. So they will exert a pressure inwards to the p-type semiconductor. Similarly, the electrons from this side will move towards the n-type semiconductor, and they will again repel with the electrons of this type of semiconductor. So what will happen? Again, this will exert a pressure because they will repel the electrons of the n-type semiconductor, and so they will exert a pressure again inwards. So from both the sides, my pressure is inserted inwards, and so my potential barrier gets reduced. So suppose my potential barrier was this, so it will get reduced to this. From both the sides, the pressure will be exerted, repelling. So from both the sides, the pressure will be exerted and my potential barrier will get reduced. My potential barrier is having a voltage EMF, say EB. And this side of voltage which is flowing in this, from which the positive terminal gets flowed and creates a voltage, say it is V in this direction. So both the voltages are in the opposite direction. So my net voltage will be V minus EB. It will be V minus EB. My net voltage will be V minus EB because V is flowing from here in this direction, and EB, we already know the potential barrier is in this direction. Okay, so my net voltage will be V minus EB. Okay, now let us see what happens to the potential barrier. So my previously potential barrier was somewhat here. It was my potential gradient. Potential gradient is nothing but a slope. It determines the slope. So previously my potential barrier was this. Previously my potential barrier was this and my potential gradient was this. So when I applied my battery, that to P terminal applied to the positive terminal and negative N-type semiconductor connected to the negative terminal. then what happens is my potential gradient gets reduced. So my potential barrier gets reduced. So my now potential barrier will be somewhat here. So this much it gets reduced. So this is my new potential barrier. So this is my new potential barrier when voltage is applied. Okay, so this is my new potential barrier. So I can see the magnitude of the new potential barrier, it is very much less. And because of this barrier only, my electrons were not able to move from one region to another region. Although these electrons were having some attraction with the holes of this p-type semiconductor, but it was not able to move from this n-type region to p-type region because of this barrier. This barrier was like a wall towards it, and it was not allowing any electrons to flow from this one region to another region. But when my potential barrier gets reduced, when I applied the voltage is applied and my potential barrier gets reduced, my electrons can now easily move, because now it is not having so much of barrier in their path. Okay, so it behaves like a resistance, because resistance is always defined as the obstruction to the flow of current. So it behaves like a resistance. So in this case, it will be having low resistance. It will be behaving as a resistive path. When it will be behaving as a low resistive path, the current will flow from this terminal to that terminal. Okay. So when I apply this much of voltage, that my V becomes equal to EB. When my E becomes equal to EB, so or V is greater than EB, then in these cases my barrier gets weakened. The hold is on my potential. So because of this potential, my barrier gets weakened, because my depletion layer gets narrowed. So what all conclusions I have? I have the conclusions that my depletion layer gets narrowed. My depletion layer gets narrowed. Also, potential barrier decreases. Okay, and then potential barrier decreases. Then the next conclusion is that my electrons can move from N to P, and holes which are positive charges can move from P to N. Actually, the movement of holes is very less as compared to the electrons. Mainly the electrons will be attracted towards these holes of the p-type semiconductor, and then they will neutralize over here, they will recombine over here, and the left out electrons will be attracted towards this positive terminal of the battery, and so the left out electrons will then move towards these. They will complete the path like this, and then another electron will move over here, then the path of the electrons will be like this. So my movement of the electron path will be like this. Okay, and I know that the current flows opposite to that of the path of the electrons. So my current will flow in the opposite direction from positive terminal to the negative terminal. So my current will flow from the positive terminal to the negative terminal like this. Okay, with this voltage V, it will flow from positive terminal to the negative terminal. Okay, let us say the current is I. Okay, let us say the current is I. So my flow of the current will be in the opposite direction as that of the electrons, as that of the direction of the electrons will be opposite of that of the direction of the electrons. So I can say one more conclusion, my PN junction behaves like a conductor, because in conductor also the current flows easily. There is conductivity of the current. There is a defined path for the current to flow in the case of conductors. So in this case, my PN junction behaves like a conductor, behaves like a junction, behaves like conductor. Okay, so in this case my PN junction behaves like a conductor. So this was all about forward biasing. In the next lecture we will be studying about the reverse biasing. Okay, please share my videos, please subscribe my channel. If you have any doubt, you can ask me in the comment section. Thank you.